So now that we know how to find concentration of a solute in a solution, what does the concentration actually affect? Are we just doing this exercise as a scientific exercise in order to just satisfy our curiosity? Or does it really have any significant effect in real life situations? The answer is, of course, it has effects. Concentration of the solute particles affect certain properties known as colligative properties, and it does not depend on the identity of the solute. So whether I dissolve salt in water or sugar in water, if I know what is the concentration of either and if they have the same concentration in two different containers where I dissolve them, then regardless of whether it's salt or sugar, there are certain properties which are affected by having them dissolved in it. And those properties are colligative properties. There are four colligative properties we will look at, and those are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. We will actually discuss three of this in this video, and then we will discuss the other one, osmotic pressure, in a later video. And needless to say, but these four properties have been used by the application of these four properties have been put in place by various industries such as the automobile industry or in a medical environment, as we will soon see. So the first one, vapor pressure. Vapor pressure is lowered when we dissolve a solute in a solvent. Now let's say that the solvent was water and the boiling point of water is 100 degrees. But when we are not at the boiling point and let's say we are at 25 degrees Celsius in a closed container in which we have some water, let's assume this green liquid is water. Of course, water is not green, but let's assume the bottle is green and that's why it looks green. And there is the empty space. In the empty space is the vapor of water, as we saw in the previous video in the last chapter, how there is vapor pressure produced by the liquid, and as the temperature goes up, the amount of vapor goes up, hence the pressure goes up. We can actually measure the vapor pressure by having this kind of a U-tube attached to our container, and inside the U-tube we may have something like mercury. And mercury, as you recall from the study of gas laws, was used by Torricelli as the liquid that was pushed out by the atmospheric pressure, and when it rose in a tube up to a height of 760 millimeter, that was equal to 1 atmospheric pressure. So here the vapor inside this closed container can also push mercury away, and there could be a difference in height here, and that difference in height tells us about the pressure, not due to the atmosphere because this is a closed container, but due to the vapor of this liquid. Now, instead of having a pure liquid, if we had a solution, let's say it was a solution of sodium chloride in water, what would happen to the vapor pressure? How high would be this height? The answer is vapor pressure would be lowered. The amount of the number of vapor molecules coming from the liquid will decrease. Hence there will be lower pressure, and so that it will not fight against this mercury as much. So mercury will not be pushed back as high, and so the height would be lower, telling us that the vapor pressure has been lowered. Now why does this happen? This happens because the solute particles are blocking on the surface, they are blocking the solvent from evaporating and entering into the vapor phase for a reason as simple as that. And we can see it here how if we assume that these white balls, or rather these white molecules that look like tiny capsules, they are solvent particles, and then when we introduce some solute shown here in red tablets, then there is less amount of the white on the surface that can actually enter into the gas phase. And because of that, there is lower vapor pressure produced by the solvent. Raoult's law states that when a non-volatile solute is added to a solvent, vapor pressure of the solvent decreases in proportion to the concentration of the solute. So notice first of all that Raoult's law does not state anything about the identity of the solute, whether it's salt, sugar, or anything else. But it does state that as the concentration of the solute goes up, the vapor pressure for that particular solvent will go down. And now this is a very, very important property that we have actually utilized in our modern world. For example, we add the radiator fluid in our cars. That's not really pure water, but it's a mixture of water and another molecule called ethylene glycol. Well, what it does is it ultimately lowers the vapor pressure of water, because now it's a solution of two different molecules which dissolve into each other very nicely, because both are very, very polar, water as well as ethylene glycol. As a result, we can add a lot of ethylene glycol to water, and so the concentration of ethylene glycol is very high in water, and as a result the vapor pressure of water goes down. So why exactly are we adding that kind of radiator fluid into our cars radiators? Why not just water? Because as the car's engine gets very hot while it's functioning, and if the radiator fluid is supposed to absorb all that heat, and if it gets very hot and if it's just water, it will start to boil and it will turn into steam inside the tubings. And once it's steam, it will not absorb heat as uh, nicely as it was previously, before when it was liquid. By converting it into a solution of ethylene glycol and water, we have just lowered the vapor pressure of our water. As a result, it will turn into steam at a much higher temperature. And so vapor pressure lowering actually brings us to the next 2 points: freezing point depression and boiling point elevation, of which I want to talk about the boiling point elevation first, because it's directly related to vapor pressure lowering. If water, for example, if we say that at 25 degrees Celsius, if pure water has a vapor pressure of let's say 300 millimeter mercury, and as we go from 25 to 26 to 27 and so on up to 100 degrees, it becomes 760 millimeter mercury. At 760 millimeter mercury, that's where it starts to boil, telling us that's the boiling point of water, when the vapor pressure of water will equal to the atmospheric pressure. But now that we know that adding a solute lowers the vapor pressure at any given temperature, and instead of being 300 millimeter mercury at 25 degrees Celsius, if it lowers it to 250 millimeter mercury, then as the temperature goes up and we are at 100 degrees, we will not have reached 760 millimeter mercury. Instead, it would be lower than that, perhaps 710 or 720 millimeter mercury. In order to reach 760 millimeter mercury, the temperature may have to go up by 5-10 degrees, depending on how much was the vapor pressure lowered. So what that tells us is that while vapor pressure is lowered when we add a solute to a solvent, boiling point is also elevated. And that's exactly what we depend on in our car's radiator, that the temperature at which the mixture of water and ethylene glycol will start to boil will be higher than if it had been pure water. And so, on a hot day or when the engine has been functioning hard and it has become very hot, we want our radiator fluid to remain a liquid and not turn into vapor. What about freezing point depression? Notice it's not freezing point elevation but depression. So if water normally freezes at 0 degrees Celsius, now that we have made a solution of it, it will freeze at a lower temperature, perhaps -5 or -10 degrees Celsius. How exactly does that happen? Well, freezing point depression may be explained considering the equilibrium between the solid and liquid states, and solute molecules interfere with the rate at which liquid water molecules associate to form the solid state. An example of this is if you live in a cold environment and where it snows, immediately after it snows, some of the county regulation says that the homeowner must add salt on the pavement on the road in order to melt all the snow away so that nobody may fall and slip and break a bone. Now, why does adding salt melt all that snow? What exactly is happening? Snow is, of course, ice or more or less solidified chunks of water that basically precipitates from cold weather. And so, when you add salt to it, you are creating a solution, of course, a solution of water and salt. But now that the freezing point is depressed, and let's say instead of freezing at 0 degrees, it freezes at -10 degrees, unless the temperature goes to -10 degrees, the mixture of salt and water will remain a liquid up to that temperature. So if it was, let's say, -2 degrees and it snowed, and you go out of your home and you add a layer of salt to that snow, it will start to melt immediately. Normally, snow would remain frozen at -2 degrees because the freezing point of water is 0 degrees. But as the temperature goes, as we add salt to that snow, now the freezing point has been depressed and it is now -10 degrees. So if the temperature remains -2 or even if it goes down a few degrees, instead of that snow turning into ice or that snow remaining snow, it will rather turn into liquid, and that way it can be washed away into the drains. So those are the two properties, freezing point depression and boiling point elevation, that arise by adding a solute to a solvent. Also, vapor point depression is the other property. I mean, rather, vapor pressure lowering is the other property. And these three are known as colligative properties, apart from one more colligative property which we will discuss later called osmotic pressure. We will look at some of the situations where we can now find the new boiling point after elevation of the boiling point once a solute has been added, and how low the freezing point goes after a solute has been added as well in the next video.